This says on page 85, says college newspaper wants to learn the average amount paid by college students on textbooks each semester. They conduct a random sample of 200 students at their college. The average amount paid was $560. The newspaper assumes an overall standard deviation of 150 to create a 99% confidence interval. All right, so our point estimate is going to be, so PE, point estimate, is going to be the 560. The critical value, we don't have yet. We have to find that. And then the confidence interval is going to be the 99%. And then the standard error, we don't know that yet. All right, so let's look at it for a few things. The critical value is going to be, what's happening? Critical value is going to be in order to find this, we have to do, that's our z-score. So this will be our normal dist on Desmos. Hey,
how you doing, sir?
Doing well. Great to see you. Great to see you.
Great to see you.
And then we'll have to go dot inverse CDF. And halfway to 100 from 99 would be 0.995. All right. So, Desmos. Hello. All right, functions, normal dist. Okay, so there's a normal distribution. Then we're going to go period. And then our inverse CDF. And we're going to go 0.995. So 2.57 will be our critical value, 2.58. That's pretty simple. So that's 2.58. And then we want to find our standard error, which is going to be, what was our equation for that?
Hey, what's up, sir?
Good to see you, buddy.
Can you go back to Desmos real quick?
Yep. Huh?
What's the z-score?
The z-score is 2.57 or 2.58.
Oh, so that's how you get it.
So then, let me just go back to 5.8 just so I can verify the equation. Hey, how are you? Good to see you. Sample 200. It's not the looking for the other one. Where's the other one? Where's my equation for it? It is average standard deviation 150. Okay, so we have standard deviation. So this is, in order to get this, we're going to go z times the standard deviation over the square root of the sample. So our z-score, our critical value, is going to be 2.58 times our standard deviation, which they told us was 150 over the square root of our sample size, which is 200. So Desmos will handle that nicely. So 2.58 times our standard deviation of 150 divided by the square root, divided by the square root of our sample size, which was 200. So 23.36 or 37. 2737. So this is going to be 2737. All right, so this is our margin of error in which we're going to go standard error of the mean. Standard error of the mean. I'm not getting my same, so this is the answer to number 2. We haven't answered this yet. We still have to get back to it. So this means that we are 99% confident that the average paid by students will be within $27.37, which means on our, for number 3, we're going to go 27.37 plus or minus. Hey, good to see you.
Hey, so.
Good to see you.
Yeah.
So 560 plus or minus that, which was our amount that we saw that we paid. So this is going to go between 532.63 and 587.37. Okay, so we're 99% confident that if we did another sample of 200 students, that we would fall somewhere within that range. Does this interval provide evidence? Does it provide evidence that the average amount of spent on textbooks? Gents, talking too much. Does this interval provide evidence that there's evidence that's spent within textbooks to students is greater than 550? Okay? So, if they're saying for number 4 that students paid more than 550, that's within that. So this is no, because again, we don't know. We could be close to this side. We could be close to this side. So someone's saying students are going to pay more than $550 per book because it's within our region. Now, if they said students are going to pay, if this number 4 said students pay more than $530, there's definitely evidence because of our system that that would have taken place. But because we're choosing something within our confidence interval, we can't make this conclusion. Okay? And then it says recalculate with a 90%. So when I do a 90%, that's going to be the normal dist. Normal dist of this, period, inverse CDF. Halfway to 100 from 90 is 0.95. And then we can just plug that in and get our new Z value. So 0.95 is here. So that's going to change to 1.64. So that's our Z score times our standard deviation of our sample. So if we work that out, which is 1.64, which standard deviation was 150 over the square root of 200. If I work that out, that's going to come, that's our confidence interval will work out to 542.55 to 577.45. Okay, so notice this was at a 99% confidence interval. This was at a 90% confidence interval. The 99%, it was a lot more broad. The 90% is more narrow. Okay? So as our confidence level drops, that means that we're closer and closer and closer to what our actual parameter, in this case of 560, would be. Okay? And that's the way it should be working. And interpret this. We're 90% confident that our textbooks fall within that region. That's letter B on 5. And then if the true amount spent by college students is not within the confidence interval, then what? If anything went wrong, explain. Okay? So if our original parameter was outside of it, like this case, we had a 1% chance that we were going to be outside of it. In this case, we have a 10% chance. So if our point estimate is outside of it, there is a chance we could be outside of it. Of course, the higher our confidence interval, then the lower chance that it could take place. But it could. It's something that could happen. And then let's see, the backside seems pretty straightforward. Okay, so let's move on. So this week, my friends, we have today 5-9, tomorrow 5-10, and then I don't really have a review set up, but I was going to just review on stuff on Wednesday that'll help you towards the test. The test will be 2 days. It's going to have some multiple choice, some written. I'm going to try and split them up between the two. And I feel pretty good that if we kind of do it together, both parts, that I think, some of you probably are much stronger understanding, some of you might not, which that's just kind of the normal thing. But it kind of pulls everybody together. We regress back to the mean, which is great. All right, so on page 19 is where I'm at. Okay, this is called a one mean t-interval. Now, a t-interval is going to be used when we have a small sample size, meaning less than 30. Okay, so we're going to we're looking at a t-interval when we're dealing with this. Okay, and I want to show you what a t-interval will look like. So I'm going to first do this. Normal distribution looks like this. Everyone agree? If I do a t-distribution, and this is a t-distribution revolves between 0 and a standard deviation of 1 as well. But if I go and I take a look at a t-distribution, notice what it says on the bottom of the screen. It says degrees of freedom. Okay, so let me describe to you what degrees of freedom would be. Let's say we had a sample of, 28. My degrees of freedom are going to be 27. Okay, let's say I have a sample of 22. My degrees of freedom, DOF, is going to be 21. If I had a sample of 3, my degrees of freedom is going to be 2. So what am I doing to find my degrees of freedom? Yeah, my sample size minus 1. Okay, now we have continued to say that 30 is our comfortable zone. Okay, that's usually our minimum. And then if we have, if we use the n times p is greater than or equal to 10, or n quantity 1 minus p is greater than or equal to 10, that's also. But there is a chance that we might be randomly selecting and we don't have a large enough population to get a sample bigger than 30. Okay, so on Desmos, it says degrees of freedom. So let's do the first one. So if I had degrees of freedom of 28, I'm going to plug a 27 in. Take a look at what my graph did. Okay, let me go away, come back. Are they pretty close? Agree? So watch this. If I made my degrees of freedom, let's say I made it like 45. Watch this, ready? It's green right now for normal distribution. Look at this. It's almost spot on. Agree? But where this gets really goofy is, let's say we have degrees of freedom of 8. See how it's kind of shifted a little bit? And as I change my degrees of freedom to be smaller and smaller, see how it's kind of tailing down? Degrees of freedom of 3, 2, 1. You see where the error is starting to take place? So that degrees of freedom thing is taken into account the variability that would take place. We are softening our normal curve to look a lot, it's coming down. It still looks like, like if I just had this up there and I said, hey, take a look at that, you'd say, oh, it looks like a normal curve. When you look at the actual normal curve, you see that normal curve is indeed taller and skinnier, and the degrees of freedom is what it's doing is it's stretching out our information. So it's fine if we now have a sample less than 30, but we have to know that once we have a sample size smaller than 30, we're going to use something called a t-distribution rather than a normal distribution. Okay? So for sample size smaller than 30, you use a t-distribution. Okay? But you have to realize this is going to be degrees of freedom. And degrees of freedom is always the sample size minus 1. That's always what it's going to happen to be. So the one mean t interval is similar, is halfway down on page 19, similar to the one mean z interval. There are two key differences. The t-distribution was created so that we may confidently substitute the sample standard deviation for the population standard deviation. Therefore, we will use a t-interval when we are required to use the sample standard deviation. Okay, so let me say that one more time. We have a standard deviation. We have two different standard deviations that can be given to us. We can do of the entire population or the sample. Oh, come on, computer. Catch up with me. And if I do the sample is going to be a t-distribution. Okay, so if you're reading something and it says, we found that our sample standard deviation is this, you know that you're going to jump right to a t-distribution. Number 2 says we do need to calculate the t-critical value, not a z-critical value. This method for doing this will be discussed later, but the margin of error, MOE, is going to be t times s over root n, where this is the sample standard deviation. Okay? This is our sample size. And then this t is going to be using our degrees of freedom to get it. So finding the t-critical value for any confidence level is tricky. Unfortunately, many graphic calculators are not programmed with inverse t. We do have it with Desmos. So to match the inverse norm function, we have to use often in this course. We should note here that some of the TI calculators do indeed have the inverse t function as part of it, but we have it on Desmos right away. Okay, so if you look on page 20, there is a table there that you cannot see. You might have to use your phone to magnify in, but it's not really necessary because Desmos is going to work for us. Okay. On that, they have the degrees of freedom on the left side, and then you have your confidence, 50, 60, 70, 80, 90, all the way up to 99.9. And again, that t-table is really too faint to look at. So let's take a look at example 1 using Desmos on page 20. It says we have a sample of 20 bicycles. Okay? 20 bicycles is not 30 or higher. So we have to go with a t-distribution. So, all right, my well-educated people, my degrees of freedom is going to be what? 19. Well, 20 minus 19, right?
Oh, I looked at 18.
Oh, okay. Okay, so a random sample of 20 bicyclists riding along Denver Trail System showed an average speed of 18 miles per hour with a standard deviation of 4. Create a 99% confidence interval to estimate the average speed of bicyclists along the Denver Trail System. The point of estimate is 18 miles per hour. That's the sample mean. So our sample mean is 18 miles an hour, excuse me, and the proper setup. So we need to find our margin of error. So we're going to go T. Oh, come on. You can stay with me, computer. T times S over root N. Okay. We are trying to create a 99% confidence interval. So what's halfway to 100? So 0.995. Come on. It's trying to write. It just faded on me. I gotta kill this now. Okay, so we're gonna go with the 0.995. So let's start plugging that in. Okay, so I'm not worried about this. I'm gonna deal with this. So we're gonna go backwards. So we had 20 bicyclists. Degrees of freedom is 19. So this is our thing. Now we could find the probability underneath here, which right now that's 100% of the population. So what we'd want to find is we're looking for to get to the 99.95. So I want this one to become 0.995. So you could either go in here and say, well, what happens if I plug in values? Like if I said -2, that's pretty close. We're at 0.96. So I wanted to get to 0.995. So let's go 2.3. I want 99.5. That's not quite enough. So maybe 5. Maybe 2.9. So I wanted 99.5. Do you feel comfortable we're really close to that? Does that seem okay? Okay. So on this, you kind of have to go a little bit better. I want to try one thing. I haven't tried this before. I just want to see what happens. I'm going to go dot, and then I'm going to go to my inverse CDF. I just want to see if that works, or see if there's another thing there. So I have inverse CDF, and I'm going to go 0.995. Oh, and it did work. Oh, this is the best day ever. Okay. So notice I used the degrees of freedom, which was the 19. Okay, so I find that if I put in, this is no longer a Z value, it's a T value because we're using a T distribution. So if I use 2.861, that becomes kind of my T margin of error. So 2.861, did my thing show up? Thought I opened that back up. So you can see how they're plugging in on the page, on page 20. They plugged the 2.861 times 4. 4 was the standard deviation of the sample divided by the square root. So they did the margin of error. The margin of error is the T times S over the square root of N. And we found that the T-table on Desmos was 2.861 times our 4, which is our standard deviation, over the square root of our sample size. Okay, notice the square root of the sample size, we don't use the degrees of freedom of 19 there. And so this is going to come out to 2.56. Vape alarm going off, feeling better. That died on me again. So 2.56. So our confidence interval will be 18 plus or minus 2.56, which is going to give me 15.44 to 20.56. That means that we are 99% confident that the true average speed of bicyclists along the Denver Trail System is between 15.44 and 20.56. Okay, so that's how your t-distribution will work. So it's a little different to think about with a t-distribution, but I think it's pretty straightforward. Let's see, 159. So let's do this. Let's do page 87, 88. And I think you can handle that. And that's all I have for you. Hey, thank you again for being awesome with the sub. Appreciate you.